last week we finally finished the Debye model, where we used all those ideas of oscillation particles, standing waves, density of states, etc., 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 etc. Now, it actually, most of those ideas that I described to you originally came not from Debye, but from a different problem, which is called black body radiation and ultraviolet catastrophe. Now, this problem of black body radiation and ultraviolet catastrophe, it's an example of a theory, it's an example of a model when we believe that we understand how the world works, and it hits us in the face because it's definitely wrong. So what is an ultraviolet catastrophe, or what is the black body radiation? So let's assume that I have a box. And this box is isolated, or mostly, we can take a small hole somewhere, but it's mostly isolated. And there are photons inside, light. Okay. So those are my boundary conditions. And inside I have photons, light, which is electromagnetic waves. Now, those electromagnetic waves, they hit the boundary of my box in different positions. The radiation or the energy of the electromagnetic wave is absorbed in the boundaries, okay, in the material. After a while, the energy has to be expelled back. Okay, so there is incoming waves and there are outgoing waves. Okay, so we have radiation that hitting the walls doing something, and then some radiation comes out of it. Okay, and it happens all the time. So actually, it happens all the time inside this black box, okay, or black body. Now, we can ask the following question. What will happen after a while? So we know that, well, our experience is that everything comes to an equilibrium. Right? So if we have some radiation inside, some radiation will enter the walls, some radiation will get out of the walls, and this will continue on and on and on and on. But after a while, the system will come to an equilibrium. Now, the moment that it is in an equilibrium, okay, I can treat it as any other physical system that I have been treated before. Great. So let's assume that I will solve this problem. Okay. Now, it is a simple model for anything else. So if you have a material, okay, if you have a material, right? Now, the material is absorbing radiation from the outside, is expelling radiation to the outside, and then eventually it reaches an equilibrium. Okay? So if it reaches an equilibrium, we can somehow understand from the distribution of the colors, from the distribution of the emitted energy of this specific object, what is the temperature of the object. Okay? Basically, the idea is as follows. So if I will look on the distribution of the frequencies of all the different all the different electromagnetic waves, so all the radiation that is getting out of this object, it's expelled by this object, radiated by this object. If I look on it on its distribution, okay, P of omega, what I will see is that according to the classical theory, is that this guy diverges with omega. Okay? So basically the classical theory, when it was applied to this problem, the classical theory told us that, well, the farther you will go with omega to ultraviolet frequencies, the more frequencies or the more states you will get. Right? So the probability of seeing an electromagnetic wave with very high omega is going to be higher and higher and higher and higher and higher. What's the problem with that? The problem is that it's not normalized. The problem is that, well, it's totally wrong. Basically, it will say, you're looking on something, and this something is just radiates huge amount of energy all the time. Now, we know it cannot be the case, right? Why it cannot be the case? There is a specific constant energy that it can radiate outside, okay? Because of the thermodynamic equilibrium, etc., etc., etc. So something really goes wrong. Now, what was this something that went wrong, this ultraviolet catastrophe? The something that went wrong is that two things. A, we cannot use classical physics in order to describe microscopical behavior, and microscopical behavior here is dependent on the fluctuations of different atoms. So we need quantum mechanics. Okay, this is part A. Part B is that when this classical physics was applied, it was assumed that we can cut matter to smaller and smaller and smaller and smaller and smaller degrees of freedom. Okay? And there is no limit to how smaller we can go. Okay? Due to that, we can have smaller microscopical particles that perform those oscillations. Those smaller microscopical particles, okay, eventually will translate to the larger and larger frequencies. Okay? So two explanations. Quantum, and they're somehow interfered with each other. So it's basically quantum mechanics. We do not really understand, or the classical failure was that they, by that time, still have no idea what exactly, how the microscopical world looks like. Okay? The first guy to solve this puzzle was Planck. And Planck, and this is where Einstein got his idea for a photoelectric effect. Planck said, well, I know from experiment how this omega looks like. Okay, so the work was concentrated on the emission of lights from light bulbs. Okay? So they wanted to save energy. And this is what concerned Planck. And they know the distribution of the electromagnetic energy that's coming from the light. They could measure it. And they knew that the real distribution looks something like that. Okay, so it goes up, it has a maximum, and then it goes down. Right? As you would expect, in order for something to be normalizable, it had to decay to zero. Okay, so let's continue this. So it's decaying to zero eventually. Now, Planck had a wonderful idea. And the wonderful idea of Planck was, well, I can derive two things. First of all, I can derive, well, those are electromagnetic waves, so I can derive the density of the different electromagnetic waves inside my, this is called the whole realm, okay, so inside my box, inside my cavity. But the other thing he said, which was really wonderful, said, in order to fix it, he had no idea why, mathematically. When he looked on the structure of everything that was developed in classical theory, said, well, the only thing that I need is to assume that each of those waves has quantas of energies. Okay? So the original idea for photoelectric effect that was popularized by Einstein, he got a Nobel Prize for this, actually arrived from the treatment of Planck to the distribution of frequencies. Okay? But Planck had no idea why. He's just said, well, I know that if I plug inside this formula, we will see in a second what exactly this formula is. If I plug inside the formula, where I assume that there is a quantized energies, okay, therefore I will obtain something that describes reality. Okay, so the solution to ultraviolet catastrophe was, well, we have to modify mathematics somehow. Okay, it's only later Einstein said, well, this means that you have quantum of energy. Okay, so how exactly we do that? And let's not go into the details what was done wrong, but let's try to solve it as we know today. Okay, so the description of the problem. I have a black box. Black box, inside of the box there are a lot of photons, which are electromagnetic waves. Those electromagnetic waves are in equilibrium with the material. Okay, so I have a system under equilibrium, and I want to calculate the average energy of all those photons inside. Okay. My assumptions, which are good for any physical questions. All those electromagnetic waves do not interfere with each other, which is fine. Why? Because I assume if they have different frequencies, they're not going to interfere with each other. I know this from Maxwell equations that there is a separability. Great, so I have a lot of particles. In this time it's not particles by photons. All of them are non-interacting and independent. Assumption number 1. Assumption number 2, so all those waves, my photons that I describe as electromagnetic waves, are basically standing waves inside the material. The system is in equilibrium, so whatever survives from the perspective of waves are standing waves. And I know what is the distribution of standing waves. So the distribution of standing waves, d of omega, we derived it for the Debye model, but actually it was first derived for this model, is V divided by 2 pi squared multiplied by omega squared. And in Debye model I had to dance around the linear dispersion relation, right? Here the linear dispersion relation already holds, so I don't need to describe why it is. And now I had 3 components of this density of omegas. What was what were the 3 components? 1 from longitudinal waves, 1 from polarization of transversal waves that were oscillating in this direction, and 1 from the transversal waves that were polarized in that direction. Okay, so basically polarization X, polarization Y, and polarization Z. Okay, so those were for what? For actual particles oscillating inside the material. Do you remember for electromagnetic waves how the light can be polarized? Can I have longitudinal waves? No. So oscillation is always in the perpendicular direction to the propagation of the wave. So instead of having 3 contributions, I'm having 2 contributions. Okay? Now, if I'm assuming that this is a vacuum, okay, if I'm assuming that this is a vacuum, so the velocity of the wave is just the speed of light. So I will have here 1 over c to the 3rd from the y direction, and I will have another contribution 1 over c to the 3rd to the x direction. And that's it. There is no z direction. There is nothing that is oscillating in the direction of the propagation. Okay? Great. This is my distribution of omegas. Now, the other thing that I need to assume is, or to calculate, so this is my partition function. My partition function, because I'm assuming that all the different particles, all the different photons with different omegas are independent, I basically had multiplication of all the different photons inside my system. How many omegas can I have? In the Debye model, I had a finite number. Debye said, I have a finite number of particles, So I have to have a finite number of degrees of freedom. Okay. Therefore, the multiplication was finite. Here, actually, well, it's not limited. I can have infinite number of different photons of different electromagnetic waves inside a system. I don't care. There is no limitation because the dispersion relation holds forever. This was the problem with the ultraviolet catastrophe. So here I have Z of I. Okay. Now, what is this Z of I was? Let's look on Zi. Zi is a summation of n goes from 0 to infinity of e to the power minus beta n h bar omega. Okay? So each photon have possible photon with specific omega I have energies n h bar omega I. Okay? So Zi is just a summation of e to the power minus beta n h bar omega I. This was the same assumption in the Debye model, right? But here it comes more naturally. Okay.
Why are we treating photons as harmonic oscillators?
So what is if you go forward, so it's backward, right? But if you look on a photon, what is the energy of each photon? It's h bar multiplied by omega, and it has, this is the quanta, and it can have several quantas of those energies. So this is the assumption that each photon can have multiple quantas or integer number of specific energies, which are h bar omega. That's it. We understand this now from quantum mechanics, but back then it was, I will explain in a second where it came from. Okay. Now, the summation of this guy, we know how to sum it. It's a geometric sum. So this is basically 1 over 1 minus e to the power minus beta h bar omega I. Okay. Now, you want to go and calculate U, for example, right? Because you can measure the spectrum, you can measure the different energies. How much oscillations do you have for each different different omega? So you need to calculate the average energy. Okay, so the average energy is minus d to d beta of log of z. Okay, so we need to compute z. We need to take a log of this z, and we need to calculate the derivative with respect to beta of this log of z. Okay, so some algebra in front of us. Now the trick over here, and this is always the trick, well, I don't know how many participants in this multiplication do I have. But the moment that I'm taking a log of this multiplicative term, I'm getting a sum. Okay? This is always the trick. You have independence of particles, no interactions. The partition function is factorizable. The interesting things are coming from free energy, from energy, etc. And it's always a log of this partition function. So always this factorization leads to a summation. Okay? Log of z equals to log of pi over I over zi, which equals to a sum over I, okay, of log of zi. Okay. Now this transition from a summation to integration. continuum assumption. We've seen this in the Debye model. Instead of sum, we have an integral. Log of z, let's write it, of omega. Right? It depends on a very specific omega, and we have many omegas. We don't have one, just single one. How many omegas do we have? Infinite. How many omegas there are in a specific interval is d omega multiplied by omega. Okay. So we count all the different omegas. We go all over the different photons inside the system. And when I say different photons, photons with different spectral wavelength, and we count them all. Okay, so omega, we have to start from 0, but unlike the Debye model, where there is a put by hand upper limit, which we call omega Debye, here it's infinite. So this is log of z. It's just an integration over all the specific z of omega, right? Where z of omega is just this guy. It's 1 over 1 minus e to the power beta h bar omega. Now you plug it inside this integral. And, well, you live happily ever after, because, well, afterwards comes a lot of math. Let's solve it. So we have an integral from 0 to infinity of log minus 1 minus e to the power minus beta h bar omega. Why do I have a minus over here? Because I'm not taking log of 1 over something. I'm just taking a log of 1 minus this guy. And I take the minus outside. And over d of omega, we have v divided by pi squared. What is this v over here? Is the volume of my box. Pi squared, omega squared, divided by c to the third d omega. Okay, the next step is to calculate minus d to the d beta. Okay. So u equals minus d to d beta of minus an integral from 0 to infinity log of 1 minus e to the power minus beta h bar omega v by pi squared omega to the third, omega to the second power, c to the third power, d omega. Any questions? Because I had 1 over c to the third and another 1 over c to the third, I had 2 over there. Okay, so if we already talking to spoke about the comparison to the classical case, what Planck recognized eventually, because for Planck it was u is equals to minus d to the d beta of something. This term is classical term. There is nothing quantum about it. You take a regular box, you say I have a distribution of standing waves, electromagnetic waves inside it, you will get this expression. So this is classical part. Minus d to the d beta, it doesn't care about quantum and classical. It's the same equation. What Planck actually understood, that he had to plug something like this log inside in order to get the correct result. So this function that stands over here, and it's based on separability of different particles, of different photons, separability of waves, but that each photon, each electromagnetic wave, have quantas of energies. Planck did not know. What he knew that he had to plug, since he need to make it fit to the experimental result, he had to plug inside some function in order for everything to work fine. Okay. in order for everything to fit with the experiments. So this was the guess. Originally, this was not discovered, it was calculated. d to the beta is known. This was guessed by Planck. Out of this guess came the idea of Einstein that we have quantas of energies. Now we simply say, oh, we have quantas of energies, so let's calculate the partition functions. Anyhow, let's continue. So this is the derivative with respect to beta, the integral with respect to omega. Nothing bad happens to this integral, so we just plug it inside, and we have u equals 2. So minus and minus are getting outside. We also can get outside, well, we won't get anything outside. From 0 to infinity, we have v divided by pi squared c to the third omega squared. And here we have 1 over 1 minus e to the power minus beta h bar omega. Okay, and on the upper side, we are going to have minus e to the power minus beta h bar omega minus h bar omega d omega. So let's write it down. U equals to an integral from 0 to infinity v divided by pi squared c to the third omega to the third h bar. Okay, and I have now e to the power minus beta h bar omega divided by 1 minus e to the power minus beta h bar omega d omega. Okay. Great. So what we have here the following. From 0 to infinity, and let's call h bar omega, we call it energy, some epsilon. So what we have over here is this epsilon. Okay. H bar omega equals to epsilon. So therefore d omega equals 1 over h bar d epsilon. Okay. So we have v pi squared c to the third h bar omega equals to epsilon divided by h bar to the third e to the power minus beta epsilon divided by 1 minus e to the power minus beta epsilon d epsilon 1 over h bar. Okay. So what we have is that u equals an integral from 0 to infinity. Here we have epsilon, and we'll just write down an epsilon over here, and you will shortly understand why, multiplied by h bar to the third, h bar to the fourth, h bar to the second, h bar to the fourth. So v pi squared c to the third epsilon to the second power divided by h bar to the third power, right? And here I have 1 over e to the power beta epsilon minus 1 d epsilon. What is U?
Average energy.
The average energy. What is written over here? What is this function?
It's the expected value of the energy.
Exactly. This is the expected value of the energy. So, what is an expected value of the energy? U equals to 0 from infinity. The expected value of the energy, so epsilon, P of epsilon, d epsilon, right? So this is the probability density function of different energies. If U is the average, and I've written it down as a summation, which is an integration because it's a continuum function, an continuum random variable, an integration over all the different values of the energy. I sign it up as epsilon, okay, multiplied by some function. This function is the density, okay, and this function was guessed by Planck. How it guessed? Well, he measured the distribution of the energies because he worked with those light bulbs outside of, and he measured the distribution. And he said, well, in order for everything to work out, it has to be this guy. Although he later on understood what it means. It means that I have quantas of energies, etc., etc., etc. So if we plot this down, P of epsilon, the function of epsilon, you have this guy. Okay. So there is a central peak, okay? And the central peak comes from the behavior of this guy. It has a behavior for small epsilons, but due to the presence of this exponent over here, eventually it won't go up like the classical theory. It actually goes down. Okay. Now, we can calculate this integral. We can get the average value. So this actual integral is solvable, and it is that takes everything out. So we have v divided by pi squared c to the third h bar to the third. Okay, and here we have an integral from 0 to infinity of epsilon to the third divided by e to the power beta epsilon minus 1 d epsilon. Okay. So we still have a dependence of beta over here. So let's take this outside. So we say beta epsilon equals to x. Okay. So epsilon equals to x divided by beta, and d epsilon equals 1 over beta dx. Okay. So if we make this substitution, the lower limit of the integral stays the same, the upper limit of the integral stays the same, and we have an integral from 0 to infinity. The prefactor is the same, v divided by pi squared c to the third h bar to the third, and here we have beta x divided by beta, I'm sorry, x divided by beta to the third divided by e x minus 1 multiplied by 1 over beta dx. Yep. Yeah. Okay, so you where this exponent get? So we take this guy and we get it from the numerator to the denominator. So we have e to the power beta epsilon, and e to the power beta epsilon multiplied by e to the power minus beta epsilon is still simply 1. Okay, so I took it from the numerator and I pushed it into the denominator. Yes.
הגרף שסיטטת זה גרף של האספקט כתלות באנרגיה, נכון?
Yes.
ואנחנו מצאנו את הדנסיטי, כאילו של ה...
This is the distribution of the different energies.
כן, אבל זה לא...
It's not exactly power. It's not the power, it's the distribution of the different energies. So if you think about it, so if you say that the average energy of each electromagnetic wave is proportional to omega, it's also the distribution of the spectral density. Okay? So it's not the power, it's the distribution of energies. Power is slightly different, but it's going to be the same. This is P, the distribution of epsilon. Okay? D, that appeared previously, there was distribution of omegas of standing waves. Okay? This is P. This is P. This is P. Okay, so let's finalize this. Okay, so we have u equals to, let's take everything that it's not related to x outside of this integral. So we have v divided by pi squared c to the third h bar to the third. All the betas that we have over here, it is what we have, beta and beta, and that's it, right? So we have 1 over beta to the fourth, okay, 1 of the beta to the fourth, and here I have an integral 0 to infinity of x to the third e to the power x minus 1 dx. This is just a number. Okay, this is just a number. And what this number is? It's a zeta function. How zeta function is described?
The sum.
So zeta of alpha equals to 1 over alpha factorial, or let's write down gamma alpha, an integral from 0 to infinity, x to the power alpha minus 1 divided by x e to the x minus 1 dx. Okay. So here we have this integral from 0 to infinity of x to the third divided by ex minus 1 dx. It equals to zeta of 4 multiplied by 4 factorial.
Wait, gamma of alpha or alpha factorial? Because those are different.
Yes. So gamma alpha plus 1.
Additive, yeah.
Gamma alpha plus 1. Thanks. Okay. So what is zeta of 4? So it's a known thing. So you're right, it's gamma alpha. It's gamma alpha. So here we're going to have 3 factorial. Okay, so this guy, zeta over 4 equals to pi squared over 90 multiplied by 3 factorial. How you calculate it? Oh, you can. So u equals to v divided by pi squared, or pi, because we're going to have pi over here.
Didn't you say pi squared in the zeta function?
Sure.
No, in the zeta function you
This is pi squared.
You said pi squared.
It's pi to the fourth.
Oh wow.
Ah, yeah. Pi to the fourth. It's pi to the fourth. So we have v. We have pi squared over here. We have pi over 4 from here, so we have pi squared. C to the third stays the same. H bar to the third stays the same. And now we have 3 factorial divided by 19, it's 15. 15. And the final thing is 1 over beta to the fourth, so k Boltzmann to the fourth, t to the fourth. Okay. And this behavior of a black body, okay, well, is known as Stefan Boltzmann law. Okay. So it's not that you only can calculate the average energy that a black body have, you can also calculate the distribution, and etc., etc., etc. So it's actually very practical for 2 reasons. The first reason is you can use it to measure temperatures, right? So if you know the distribution of of the energy, okay, that is coming out of a specific body, you can measure because it's emitted outside. Okay? So the moment it's emitted outside, I can measure the energy that's coming from this bulb over there. I can measure it standing over here. I can fit the distribution of the absorbed energy in my device. And from fitting whatever I got there to this function, look, it depends on beta, it depends on temperature. I can actually measure temperatures. Okay, so you know that somehow the published result about the temperature of the sun, the temperature of different stars, and actually more related, we have thermometers that point out at you, okay, they're pointing at you and saying your temperature is 36.6 Celsius. How do they do that? Okay, how we know the temperature of distant objects? Because of this behavior. Okay? So we assume, you can complicate the model a little bit, but this basic assumption is, well, whatever is emitting energy is in some sort of equilibrium. And in this equilibrium, I know the distribution of the radiation with respect to the temperature, the beta that stands over here. So the only thing that I need to do is to absorb enough energy, okay, in my device, build a histogram of the spectrum of whatever I'm getting, of the energies, and then I'm done. I fit it to my function, or even simpler than that, I find the maxima, okay, and I find the maxima of this function, and from this I determine what the temperature is. Okay? So it's a very applicable thing, and it was used in astrophysics again and again and again, of course, by complicating this basic model. Okay, so because we need maybe to introduce additional assumptions regarding what are the distribution, what is the equilibrium of a star. Okay? It's not exactly a black body, but it's not really far from that. The second major thing that came out of it was it supported the theory of Big Bang, of how this universe started. Okay? So, those are ideas. One of those ideas are, well, we have galaxies that moving around us. Okay, so and there is a redshift for this galaxy, so everything is spreading in different directions as if there was an explosion. But there a much stronger claim for this theory of Big Bang. Okay? And this is the this is a cosmic microwave background. Cosmic microwave background. Okay. So think about Big Bang. Okay. We had nothing, and then we had a huge splash of light, okay, out of nowhere, something that comes from nothing, and then this light, okay, started to spread around, and it started to cool down. Okay. So the chain of events is as follows. There is Big Bang. The Big Bang causes the expansion, so everything starts to spread around. It's not that it was in an empty room. Think about everything as just as if I had a clamped piece of paper and everything starts to expand together with the paper. It's not that the paper is located somewhere, but the paper is expanding, and I'm looking at what happens on the paper itself. So we have expansion. After this expansion, universe is cooling. So during this expansion and during the cooling, so we have particles. We have light. Okay? Some of this light is converted into other particles. So due to this cooling, we have photons plus hydrogen, plasma. Okay? So we have a lot of atoms, okay, and we have electrons, and we have neutrons, and we have protons, but they are not combined together. Okay? Electrons separated from neutrons, from protons, etc., 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 etc. Now, these photons interact with the electrons. They interact with everything else. Okay, so they somehow feel each other. They transfer energy from one to each other. Great thing. Everything in some sort of an equilibrium. The next step, again, cooling down, because everything is expanding. As when the gas is expanding, it's cooling down. Plus hydrogen atoms. Some point, some proton combined with some electrons, and they combined the first hydrogen atom. And then another, and another, and another, and it happened pretty fast because everything cooled down. Great thing. Now, what happened to all the photons that were in equilibrium with all those electrons during this stage, when we had plasma? Suddenly, all those electrons that were interacting, we had matter, we had light. Suddenly, all this matter that was interacting with the light disappeared. It's not disappeared, it's there. It's combined with protons. This will be taught in quantum mechanics class. So there is an excitation energy of hydrogen atom. What is this excitation energy? How much energy do I have to transfer to the electron to bring it from ground state to the first excited state? Several electron volts. Okay. What happens to all those photons that doesn't have this sufficient energy? They did nothing. And they do nothing till this day. So if we go and measure, and it should be everywhere around us, but those photons, since they cannot excite hydrogen atoms, they cannot do anything. They just pass through everything as if it was thin air. Okay, but vacuum, basically. They don't see those hydrogen atoms. So all those fluctuations, radiative fluctuations, should be around us. Moreover, because we assume that everything is in equilibrium, their distribution should be exactly, but exactly to the any decimal point that you can assume fit the black body radiation theory. And in 1958, I think it happened. Two guys, Zeiss and I forget the other name all the time. What's the other guy's name? Zeiss and Wilson. And they measured this radiation all around their antenna. And they found out that it exactly fits. So it's coming from all different portions of the universe. And it has exactly the same distribution as the black body. So this is the second, but the strongest evidence for the theory of Big Bang. Why we believe in this Big Bang? Because we have evidence that's coming down from the distribution of equilibrium of some photons that exist to this day. Okay, so sorry for taking your time, and I'll see you all tomorrow. Thank you.